Welcome back. In the last module, we talked about how to perform hypothesis tests when we had a population proportion or percentage. This week, we're looking at how to do hypothesis tests when we have a population mean. So here we're working with a quantitative variable. We're also going to discuss very briefly how to do a hypothesis test on another parameter for a quantitative variable, which is the population standard deviation. Before viewing this video, you should do two things. First of all, make sure that you download and open up this PowerPoint because you're not going to be able to do the reading quizzes if you don't. And secondly, go ahead and open up StatCrunch because we're going to use that also. So you might want to pause the video and do that right now. So the heavy machinery in this section is the central limit theorem, just as it was for our work with the population proportion. And we're going to see that there are, in a sense, two versions of the central limit theorem, one which we use occasionally, but it turns out it's very helpful for us to kind of get our intuition as to what's going on, and the other which we're going to primarily use, and it's not so obvious where it comes from, which is why we go through the first version. So the first version involves a situation where we know the population standard deviation sigma. And when we want to use the central limit theorem, just as we had to do for population percentages, we have to make sure that our sample is quote unquote good. And when we're working with a quantitative variable, a good sample has to satisfy two conditions. First, it has to be random, just like it had to be for the population percentage. But there's another condition that's slightly different than when we worked with population percentages. With population percentages, we only looked at the sample size. However, for quantitative variables, either a large sample can suffice or a variable that has a normal distribution will suffice. So we have to make sure that one of these two conditions are satisfied. Either our sample size is at least 30, and you could make that greater than or equal to 30. The 30 doesn't really matter in and of itself. Or the variable has a normal distribution. And when we're working with very small data sets, we're talking like maybe on the order of 10 or less than that, it's very hard to tell visually if the variable has a normal distribution. So normally, we just look to see if it's kind of symmetric and mound-shaped. In the same way that we rarely have a true random sample, in the same sense, we'll be satisfied for something that we think is representative of the population. In the same sense, if our data is kind of unimodal and somewhat symmetric, we'll say that suffices for normality. Now, these are just rules of thumb as far as a sample size goes. This sample size of 30 works well if the data is not strongly skewed. However, if the data is strongly skewed, you have to use a larger sample size. And how large? Well, we're not going to get into that because that's going to deal with more technical details than we want to, get ourselves involved with. So usually 30 is okay. Generally, a sample size of 100 pretty much guarantees that for most data sets, even ones that have pretty strong skew, you can still say the central limit theorem is satisfied. But for our purposes, we're going to assume that 30 is okay. Now, if we check those two conditions and they come out okay, then the central limit theorem tells us, and we saw this actually from the sampling distribution, that X bar has a normal distribution, it's centered at the population mean mu, and its standard deviation is given by the population standard deviation of the variable divided by the square root of the sample size. And so just like when we were looking at the sampling distribution for sample percentages, and we saw the sample size came in to the standard deviation, like 1 over the square root of n, we're seeing that same thing for sample means. Now here's the twist that we're going to add here. We said before that if any variable has a normal distribution, its z-scores have a standard normal distribution. So if I go ahead and subtract off the mean mu and divide by the standard deviation of x bar, these z-scores have a standard normal distribution. And you want to recall what standard normal means. It's a specific type of normal distribution, specifically one that has a mean of 0 and a standard deviation of 1. And in the context of a hypothesis test, we're going to call this z-score a test statistic. And we'll come back to this term as we're working problems. Now there's a problem with saying that sigma is known, and that is that we rarely do know sigma. If mu is unknown, the population mean is unknown, what is sigma? Well, if we said it's a measure of the average distance of the rest of the values from the mean. Well, if we don't know the mean, how can we get this average distance, right? So we generally don't assume that we know sigma. There are some special situations where we do, but we're not going to work with those. So instead, we're going to assume that we only know the sample standard deviation, which is small s. And that's what we're going to use in our problems. Now, when we go to apply the central limit theorem, before we can use it, we have to check that the conditions are satisfied. And these two conditions are exactly the same. And generally, like I say, we drop normal distribution for basically symmetric mound-shaped. That's generally good enough. In the same way that a representative sample is good enough for being random, a symmetric mound shape is good enough for being normal. But our sample size condition is still the same. Now, the central limit theorem tells us something a little different here, okay? It says that we're going to compute a new statistic, but instead of a z-score, it's going to be called a t-score, hence the small t. And we notice that it's exactly the same as the z-score, except in lieu of the population standard deviation, we use the sample standard deviation, which makes perfect sense because the sample standard deviation is an estimator for the population standard deviation, the same way that the sample mean is the estimator for the population mean. And this is going to be the test statistic that we're going to use in our hypothesis tests. And these t-scores, they do not come from a standard normal distribution. I'm going to just mention that they come from something called a t-distribution, which also has a mean of 0, but it's not quite a bell-shaped curve. It turns out that its tails are a little fatter than a normal distribution, or a standard normal in this case. So it looks like a standard normal, but it's not quite. Okay. There are some variations we're going to have to think about, and some issues that we're going to have to consider, which we didn't have to think about when we were dealing with a population proportion hypothesis test. And the one issue that can arise is whether we want to use the z-score or the t-score. And again, that's based on the question of whether you're given the population standard deviation or the sample standard deviation. Sample size is going to be important here, and it's going to be important primarily when it's less than 30. When it's less than 30, we're going to have to do something that we didn't have to do when we were talking about hypothesis tests on pi. We're going to have to somehow determine if the data is mound-shaped and symmetric. And we're going to talk about two ways that we are going to figure that out. And finally, we have to ask ourselves whether we have data or whether we're given summary statistics in the problem statement. And this we actually did do when we talked about hypothesis tests for pi, right? So sometimes you're given a data set and you open it up in StatCrunch, you're going to run the hypothesis tests, and you're going to have StatCrunch compute the sample size, sample standard deviation, and X bar for you. And sometimes you're going to be given the summary statistics. In other words, when you read a research paper, for example, it's very rare they actually show you the raw data set. They usually summarize the main statistics that you're going to be using when you're doing your analysis. And as we said, we're not going to have to wrestle with this question of whether we're going to use a z-score or a t-score. We're going to stick just with t-scores, assuming that we don't know the population standard deviation. So this is going to be the first reading quiz. I want you to look at this and answer these questions. This is one reason why you want to open up the PowerPoint so you're able to look at these options. And you're just going to answer, A, B, C, D for each of them, or in the last case, A, B, C. So go ahead, take a minute, and complete that. Okay, good. So here's our first problem. I'm going to work through some sample problems like you might see on the homework also to kind of explain the various sorts of things you're going to have to do and how you want to set up the problem. There's definitely some work you have to do in kind of, setting up the problem initially and understanding what's going on. Okay, so we're told that 12 different video games showing alcohol use were observed. The duration times of alcohol use were recorded with times in seconds, and they're given in the data set here. And you can click on that and open that up. What requirements must be satisfied to test the claim that the sample is from a population with a mean greater than 80 seconds? Are the requirements all satisfied? Okay, so first I want to point out that whenever you're doing these tests, okay, rather than try to just plug and chug, it's good to answer some basic questions. So with context, the first question we want to answer is, what is the parameter here? And so we're going to be looking at language. We're either going to be looking for a percentage or a mean. So in this case, I see the word mean. So I know that my parameter is the mean. Mean of what? That's my variable. Okay. So it's the mean greater than 80 seconds, okay? And this is a time, and so this is the duration times of alcohol use in video games. So it's the mean of time alcohol use was shown in video games. And obviously, our population is all video games. Okay, so now I have an idea of what's going on, okay? So let's go ahead and let's go ahead and assign values to quantities here, okay? We're only given one quantity, which is just the time, okay? We want to test the claim that the sample is from a population where the mean is greater than 80 seconds. So what is the 80 seconds? The 80 seconds is a mean. Is it a population or a sample mean? So you have to ask yourself, where did I get this value? Is it associated with a sample that was taken? Or am I given that it's from a population? And here we're told that's from a population. Okay, so 80 is going to be equal to mu, our population mean. So now we have an idea of what's going on, right? we're going to check the conditions for central limit theorem. So again, what are we checking? We're checking to see that our sample is random. And we're either going to have to check that n is greater than 30 or data has, and I'm going to say normal, but I'm going to use normal and symmetric mound shape interchangeably. Okay, for small data sets, it is really hard to definitively say it's normal. Okay, so I'm going to use the word normal and symmetric mound shape interchangeably. Okay, in the same way that I'm going to say random and representative sample are equivalent, because either one's going to suffice. Okay, has normal distribution. Okay, first of all, is there any information given here that tells us it's a random sample? No. And here you have to be careful. The book is not always consistent with how it uses this condition. But here, because they're making a point that they're checking the conditions, they're going to make an issue of it, okay? So here we don't have evidence that it's random, okay? We don't have 30 data values. Okay, so the answer to this is it random? We're not given any evidence that it is. Is it greater than 30? No. The sample size here is 12, right? So now we have to check and see if it has a normal distribution. And this takes a little bit of time. This can be a little time consuming, and I want to step through this carefully. So again, when it's less than 30, the only way we can do the hypothesis test is if the data is symmetric in mound shape, which we're going to also say normal. And the big question is, how do we test to see if the data appears to come from a normal distribution? And it turns out that there's two ways that we can do it. Some types of data we can automatically assume has a normal distribution. And we talked about this before. We said that when we have physiological data, that is, whenever we're taking measurements from a population of adult humans, like blood pressures, for example, heights, okay, concentration of chemicals in the bloodstream, any sort of measurements made on the human body generally tend to have a normal distribution. Deviations from manufacturer's claims. So if you go home tonight and you get 20 boxes of Raisin Brands and it's advertised they're 16 ounces and you weigh each of them, okay, you're going to see that they're not all 16 ounces. They have a kind of normal distribution about the mean. And lastly, standardized test scores. So IQ, SAT, ACT, these in fact do have normal distributions. But very often we're working with data that doesn't come from one of these three classes. And so what do? There are two options that we have. First of all, we can plot the data. Now you have to be a little careful plotting, and this is a little tricky. If you have a very small data set, you cannot make a histogram. So between 20 to 30, usually you can make a histogram. Below 20, I would suggest you make a dot plot. Again, exploratory data analysis, so it's not a bad idea to plot both. And so let's go ahead and do that for this example, okay? So here's my data set, and this is my data set in StatCrunch, and I'm going to make a dot plot. Okay, graph, dot plot. I have 12 data values. That's way too small to make a histogram. And I'll show you really quick. If we made a histogram, this is what's going to happen. Put the mean and the standard deviation in. Okay. And you can see it's very hard to tell. The values are all kind of bunched up. Okay. You can play around with the bin width, a little bit. So you could do that. But again, unlike most usual data sets, when they're big enough to actually make a histogram, changing the bin width can change things a lot. So 10 is definitely too small. And I could try to play around. And again, I'm not going to do this. I just want to show you how difficult it is to use a histogram when you have really small data sets, and why we don't. And you can see that it's very, very hard for me. And there's a reason why. You don't have enough data values to kind of fit a nice smooth curve. There's not enough things to fill up the bins so that you have enough, okay? And I could sit here all day and play around with this, and it's going to be almost impossible to fit to anything remotely nice. Okay. So we go to dot plot. Click on your variable. Not a bad idea to click on the mean and median. Okay. If I have skewed data, that's going to come up with a mean and a median. And that's specifically true for small data sets. Outliers are really strong skew, right? And here we can see that it definitely is not symmetric. Okay? And you can see that several ways, okay? If it was symmetric, and I want to go through this slowly, okay? If it was symmetric, there would be roughly the same number of data values on both sides of the mean. So remember, this is the median and this is the mean. You can see what's happening. First of all, there's an outlier. And that outlier is drawing the mean. So when you have an outlier, it's not going to be considered normal, right there. However, even without that outlier, it would be unlikely. And I'm going to go ahead and take out the outlier and replot it. And there's a good chance that it still will not be normal enough. Whoops, I didn't put my we'll see. It might be. There's a possibility, but it might not be also. And you can see even with the and you have to put them on the same scale, right? So I'll try to get them on the same scale here. Even on roughly the same scale, there'd still be evidence that it wouldn't be normal. And the way that you judge that is, if it came from a symmetric mound-shaped distribution, okay, there should be roughly the same number of data values on both sides of the mean. And here we have 3, here we have 1, 2, 3, 4, 5, 6, 7, 8. So there isn't. And you can see that it appears, and again, we're reading into the tea leaves a little bit here, okay, because it's a small data set, but there does appear to be more like a skew here. All right. So there's evidence no matter how you slice it. First of all, just because of the outlier alone, that automatically disqualifies it from being symmetric mound-shaped. But even without the outlier, there'd still be evidence that it isn't. Now the question is, how would you know for sure? Okay? So suppose you said, I really can't tell. And we don't like this reading into tea leaf stuff, okay? We don't, we want to read graphs properly, but we don't want to read into them too much. And so this is this plot again, and I'm showing the outlier, and clearly it's not going to be symmetric mound shape. There actually is a test for testing to see if the data appears to come from a normal distribution. And this is built into StatCrunch, actually. And I want to show you this test. So these are called hypothesis tests for normality, and there are many of them. We're only going to look at one, okay? And so here it turns out the null distribution would be that the data values do appear to come from a normal distribution, and the alternative is that they're not. And so how do we do this in StatCrunch? Well, we open up StatCrunch, and we click on Stat, and then in the menu, we choose Goodness of Fit. And then we go to the little sidebar and choose Normality Test. And when you click on Normality Test, a new window will open. And all you have to do is select a variable like you do when you're plotting or doing any sort of hypothesis test or summary statistics, and you click Compute. That's all you have to do. And then a new window will appear. And this is the output. And what you're primarily looking at is the p-value here. So this is a specific type of goodness of fit test. It's testing to see if your data it fits well. That's what goodness of fit means. fits well to a normal distribution. Some of you have noticed that when you plot your data for a quantitative variable, there's an option to let you overlay the best fit normal distribution. That's kind of what this is doing. And it's looking at the discrepancy between the best fit normal distribution curve and your data. I won't go into the details of that, but that's what it's doing. And we interpret this p-value. We make our decision exactly the same way we do for any hypothesis test. We always assume an alpha of 5%. And if the p-value is less than alpha, we reject the null. And if we reject the null, that means we go with the alternative and we say it's not from a normal distribution. And if the p-value is greater than alpha, we fail to reject the null. In other words, we stick with our original belief that it is from a normal distribution. In this case, you can clearly see the p-value is way below 0.05, which is 5%, which is consistent with our original, decision that it doesn't appear to come from a normal distribution. And just for fun, I'm going to go back and rerun the test with that outlier. What would happen if we did it? Let's just see if this is our outlier here, right? And let's just rerun the test. So stat, goodness of fit, normality. And notice that we still reject the null. Again, consistent with our original decision that it did not appear to be symmetric mound shape. The p-value, which is around 0.01, is less than alpha, which is 0.05, so we reject the null. And we say that it's not from a null distribution. And so I would use this only when there's some ambiguity. And generally, again, you'll find that everything will be self-consistent. But with small data sets, it's very hard to tell. There are various types of hypothesis tests. I'll mention this very briefly. Okay. There's the Anderson-Darling and the Shapiro-Wilks. The Anderson-Darling is more discerning. In other words, it makes it harder for it to be a normal distribution. And if I click on Anderson-Darling, you'll see the p-value. Actually, here the p-value did not go down. That's interesting. Usually with Anderson-Darling, the p-value will go down. It tends to be more discriminating. Whereas Shapiro-Wilks is Shapiro-Wilks is really just testing for the difference between symmetric mound-shaped and normal. It's not being that picky. And it's interesting, in this one case, Anderson-Darling actually gave me a p-value that was higher. That's unusual. Okay. So, but we're not going to mess with that field. You don't have to change that. Okay, so now we can go back to our original problem, right? Which was figuring out what was going on. So are the requirements satisfied? Well, they don't come from a simple random sample. We weren't given that, so we can't click that. The population is normally distributed, or n is greater than 30, or both. No. At least one observation must be above 80. I'm sorry, which requirements must be satisfied? I'm sorry, it's actually the first two, right? I was thinking which ones were satisfied. Okay, so this is just checking the first two conditions right here. Right. So it's just the first and the second. Are the requirements all satisfied? Well, no. Okay. So first of all, we can rule out the ones where it says yes. So we can plumb rule them out. So we don't have to look at this one, so it won't distract us. Okay. And we'll make it really heavy so we just don't have to even look at it. Okay. And again, this yes, take that out. The first one says, no, the conditions for a binomial distribution are not satisfied. Well, we're not interested in the binomial. That's something we're going to learn about later. So we can take that out. We're interested in the normal distribution here, right? Okay. And again, the same thing here, binomial distribution. We're not interested in that. They're putting that in as a distractor, okay? Or sometimes people have studied some statistics and they say, oh, I recognize binomial. Yeah, you're good, congratulations, you recognized it, but you don't understand what it means, right? So let's see the last two. No, the sample size is not greater than 30. Check. The sample does not appear to have a normal distribution. Check. And there's not enough information to determine whether the sample is a simple random sample. So that looks to be okay. So we'll put a box around that, tentatively choosing that. And we're not saying that it's not a simple random sample. We're just not told, right? And generally, we don't like to assume things. But again, I'm going to throw out this caveat that you have to be careful with the book. The book it kind of plays loose and fast with these conditions. If I was making a homework set, I would try to be consistent, and the book is not. So sometimes they'll expect you to check if it's a simple random sample, and sometimes they won't. And you just kind of have to intuit from what they're answering. The fact that they're concentrating, okay, on the conditions for the central limit theorem means they're going to be checking. But in a general problem, they might not, and sometimes they don't. Okay, let's see. The sample size is not greater than 30 on F. Okay, that checks. The sample doesn't appear to come from a normal distribution. Yes. And there are no observations above 80. Well, that last condition is not one of the ones that we check, right? We don't check to see if there's a value above or below the mean in order to use the central limit theorem. What they should have in lieu of that is that the sample appears to be random, and they don't. So it's not going to be F either, and therefore our answer is going to be C. All right, good. Now, when you go through all this, you're not going to go through, I'm explaining this for the first time, okay? These problems take a little bit of time, but usually 5 minutes or so, but not that long, okay? All right, moving on. Okay, problem 2. Park officials make predictions of time to the next eruption of a particular geyser and collect data for the error in minutes in those predictions. The display from technology available below results from using the prediction errors to test the claim that the mean prediction error is equal to 0. Comment on the accuracy of the predictions. Use alpha equal 0.05 significance level. And then they want us to identify various things from the output. Okay, first of all, context. We see the word mean, right? Mean of what? Mean of eruption times. Mean of all eruption times from a particular geyser. That's our population. So the context here is that we're looking at for all eruptions from a particular geyser. Okay, so now we know what we're looking at, okay? Let's see. Whoops, geyser misspelled. Yeah, here we go. Okay, assign values to quantities, okay? Well, the only quantity we're given in this problem is alpha, so we know that our significance level alpha is 5%. Okay. Check that the central limit theorem conditions are met. Well, again, we're not told that it's random, so this is a classic case. Okay. And so based on problem 1, you shouldn't do the problem. Based on problem 2, they're going to say go ahead and do it. So we don't know that it's random, right? There's nothing in this problem statement to tell us that it's either random or representative. Okay. But we're going to assume that it is. What is our sample size? Well, our sample size is a little tricky. So here, the sample size is 1 plus the degrees of freedom. Okay? So when you're given the output, n is equal to this thing called df plus 1. Okay. So this degrees of freedom is 1 minus the sample size. Okay, so this thing df here is called the degrees of freedom. And we're not going to worry what it means, okay? It's not We don't want to go that far into the weeds, trust me. But this DF is called degrees of freedom, and you simply add 1 to get the sample size. So we know that we're okay, right? We have no problems because we're going to get 99 in this case when I add 1 to 98. So again, according to the book, they're kind of assuming that it's random, even though it's not being said, and our sample's above 30, so we're okay. What is our hypothesis? Okay, the claim is that the average of the prediction errors should be equal to 0, right? When we're testing a claim, the alternative is that it's not equal. It's the opposite of the claim. Okay, so here we're claiming, and so the claim is going to be the null hypothesis. Is that mu is equal to 0. When we test the claim, we're saying the opposite is true. And this is the alternative. I'm just going to type not equal, NE for not equal, okay? There is a symbol for this if you want. Here, I'll put it in really quick. But you can just type not equal, it's not a big deal. So these are our hypothesis, okay? Okay, so now we're ready to start kind of taking this apart, right? So we've identified the null and the alternative. And again, thinking about what we're doing, whether we're testing a claim or we're seeing if a change has occurred, those are the two scenarios, right? Helps us put everything in context. The test statistic, well, this is your observed t-score. So this is our test statistic right here. So we mentioned how t-scores are test statistics, and you see t observed, that means that's the t-score from your actual data set. Okay. So this is what we want right here to make this connection, all right? So our test statistic is going to be our observed t-score right here. Okay? Our p-value is given. Okay, it's less than 0.0001. So state the final conclusion. Well, it's the same as every hypothesis test, right? Alpha is 0.05. The p-value, which is way less than 0.0001, which is therefore less than 0.05, implies that our p-value is less than alpha, so we reject the null. Okay? And therefore, we are going to decide that the mean prediction times are not equal to 0. All right? Okay, good. Notice that, so one thing to think about is the t-scores are kind of like the z-scores, okay? They tend to be a little larger. But if that was a z-score and you were minus 7.8, right, standard deviations from the mean, that would be super unlikely, right? And even for a t-score, even though they tend to be a little on the larger side as far as magnitude, nevertheless, minus 7, once you start to get around minus 5, for sure, minus 4, minus 5, you automatically know game over. The t-score is too large, you're going to reject the null. And hopefully now, one of the things that I like a lot that I see people doing is they're thinking in terms of z-scores a lot. And so you could think of a t-score as like an approximate z-score because you're using the approximation for the population standard deviation. And all that nice thinking that you've developed for z-scores goes right over to t-scores. Their interpretation is very, very similar. All right, great. Okay. So I want you to go ahead and answer the following First of all, I want you to start off and kind of flow the problem, figure out the context first, assign values to quantities, check that the conditions are met, and after you've done all that, then you can answer the first question, which is identify the null and the alternative hypothesis. So I'm going to let you pause the video, do all that. So let's take a look at this problem, okay, and try to kind of puzzle through it. Okay, so it says, in the test of the effectiveness of garlic for lowering cholesterol, 49 subjects were treated with raw garlic. Cholesterol levels were measured before and after the treatment. The changes before, minus after, and their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 2.43. We want to use a significance level of 1% to test the claim that with garlic treatment, the mean change in LDL cholesterol is greater than 0. Okay, so in other words, we're testing to see if the mean before minus after is positive, which would mean that the garlic reduced the cholesterol level. Okay, so let's first of all determine the context. Okay, let's kind of take this apart first of all. So we're looking at a mean. Okay, that's our population parameter. Mean of what? Well, it's going to be the mean of the LDL cholesterol level. This is my variable. What is my population? Cholesterol level in who? Cholesterol level probably in adults. We're going to have to assume, right? Okay, it doesn't say. It should, but it doesn't. So this is our whole problem. We know what the parameter is. It's the mean. Mean of what? That's my variable. Mean LDL cholesterol levels in whom? That's our population in adults. So let's go ahead and start assigning values to these quantities. Okay, so first I see the number 49, and that's the number of subjects, which tells me that's my sample size, right? Okay. So I know here that n is equal to 49. All right. We're given a mean and a standard deviation, right? So we have a mean of 0.4 and a standard deviation of 2.43. And we have to figure out which mean are we talking about. Is this a population mean or is this a sample mean? Is this mu or is this x bar? So we have to look. What is this the mean of? It's the mean in the changes in their levels. Who does their refer to? The people in our sample, right? So here we know that x bar, our sample mean, is equal to 0.4. And again, the standard deviation, again, comes from the sample also. So S, which is our sample standard deviation, is 2.43. All right? So these are our values that we're going to need. Now we have a good handle on what everything in this problem means, right? So are the central limit conditions met? It says assume a simple random sample's been selected. So check. Okay. So again, we're going to go through the conditions, right? Are they random? And we're told to assume that they are, right? And is our sample size large enough, or does it come from a normal distribution? Well, in this case, we probably have both satisfied, right? We know for a fact the sample size is greater than 30. So we're automatically okay. We can stop there. But we also know that we're taking physiological measurements. Okay? So even if the sample size was less than 30, we could probably still get away with assuming that it's normal. That's good. So let's state the hypothesis. So again, you want to read, what are we trying to do? And usually, it's the problem question that's going to tell you what the hypothesis is. That's the research question, right? And it's very often bundled with the significance level, because they're going to say, use this significance level to, and then they're going to tell you what the research hypothesis they want you to test. So here's my significance level to test the claim that with garlic, the mean change is greater than 0. Okay. So here we're testing to see if it's greater than 0. You have to be a little careful here, okay? And this is a situation where the book is a little off base here. So we said usually with claims we assume the opposite, okay? But this isn't the manufacturer's claim. So here we're actually testing. This is the research hypothesis. We're testing to see if the mean change, if the mean is greater than 0. One of the ways you can tell, okay, so let's go ahead and kind of flesh this out a little bit, okay? So the null H0 is going to be that mu is less than or equal to 0. And what we're trying to prove here, the alternative, is that mu is greater than 0. And what can seem confusing, and this is where I don't like what the book is doing, but what can seem confusing is the fact that we said whenever we're testing a claim, we do the opposite. That's the alternative, okay? So the claim here is that it's greater than 0. However, here's how you know this is not what's going on, and this is important. Remember that the data is always in favor of the alternative. This is important. So the reason why I know unequivocally that this is true, besides the fact that this appears to be the research question I'd be interested in, is the fact that if I'm testing to see if the mean is greater than 0, the sample mean better be greater than 0. Okay, if I was really testing to see if it was less than, and the sample mean, so if this was greater than or equal to 0, and the alternative was less than 0, and I got a sample mean greater than 0, I would never even run the hypothesis test. So you have to realize, and this is an important point, is that the sample mean has to be consistent with the alternative hypothesis. Okay. In other words, in order for me to have an alternative where the population mean is greater than 0, there has to be evidence for that. The sample mean also has to be greater than 0. So you want to be careful with that, okay? Okay, so let's see how to actually run this now in StatCrunch, okay? I have all this information that I need. I'm going to go ahead and enter this in StatCrunch. So here we go. I'm going to open up a new data table. So I have a nice clean slate. And I'm going to go down to t-stats. So when I'm running a hypothesis test on the mean, and I'm using the t-score, I'm going to use t-stats, and I have one sample. And here, I'm using the summary statistics. I'm not using the actual data. I'm given the summarized version of the data set. So let's go back and put all of our values in. So this is 0.4, right? Our standard deviation was 2.43. And our sample size, let me just check and make sure, it's 49. Okay. And the alternative is I'm testing to see if it's greater than 0. So that's how I'm going to run this particular test. put in my sample mean, my sample standard deviation, my sample size, and I put in the value, which in this case the default is 0, so it happened to be the default value, and then set the alternative correctly. So if you're not given a data set and you're asked to run a hypothesis test, you know that you need these pieces of information. Okay, so you can kind of also, reverse engineer it. If you didn't go back and figure out the context the way you should have, you can still kind of go back and reverse engineer it. You know those values have to be somewhere. And we click compute. Okay. So again, these are our hypotheses. This is our sample mean. This is the sample standard deviation divided by the square root of n. That's the standard error. Again, degrees of freedom is 1 minus the sample size. This is my test statistic, 1.15. It's the t-score. It actually stands for the t statistic, but it also just happens to look like test statistic, okay? But this is our test statistic, 1.15. This is our p-value, 12.75%. So I'm testing at alpha 1 at 1%, right? So if I go back and look at the problem, alpha is 1%. So 1%, my p-value is greater than alpha, right? 1% is less than 12%. So p-value greater than alpha, we don't reject the null. Okay. So we would decide that there is not sufficient evidence to claim the alternative, which is that the mean cholesterol level adults, the mean, and this should actually be change in, we're looking at the change in LDL levels. Okay. And notice as you go through, your understanding sometimes becomes a little more refined, right? So I would say that there is, at a significance level of 1%, there is not sufficient evidence to support the claim that the average change in LDL cholesterol levels in adults after they get garlic treatment is greater than 0. Okay, good. All right. So now let's go ahead and work a problem where we're actually given a data set. So here is a problem where we're given the data set. I'm going to go ahead and download this and put this in Google Sheets. And then go ahead and copy and paste this in StatCrunch. Okay. So I can open up another table if I want, and I will. And I can paste this in. Okay. Okay. So listed here are the lead concentrations measured in different traditional medicines. Use alpha of 1% significance level to test the claim that the average lead concentrations from all such medicines is less than 16 micrograms per gram. Assume the sample is a simple random sample. Again, so context. Always start off with the context. Okay, I'm interested in the mean concentration. Okay, again, mean of what? Okay, mean lead concentration for all such medicines. Okay, so the mean lead concentrations in all traditional medicines. Notice that we have very few values that we have to assign to quantities. We're given the significance level. What is this? Well, let's ask the question. There's only a couple things it can be, right? It can be a mean, a standard deviation, or a sample size. Is it a mean? Well, it's associated with a mean. Does it come from the sample? No, it comes from a population. So chances are this is the value that we're going to test under the null hypothesis, right? Okay, so this is a significance level, and this is probably going to be mu sub 0, right? The mean under the null hypothesis that I'm testing. All right, assign values to quantities. We've done that. Check the central limit theorem conditions. We're assuming it's from a simple random sample, so they did a good job here doing that. And now we have to check and see if the other condition is met. Do we have 30 data values, or do they at least appear to have a mound-shaped symmetric distribution? So let's check it out. We do not have 30 data values, so I'm going to check to see if it's mound-shaped symmetric. I'll make a dot plot. I have 10 data values. It's way too small to make a histogram with. And I plot those. And there's some discrepancy between the mean and the median, but if you look at it carefully, it's really not that big. I mean, this is 5 here. Maybe this is about 2. So it appears to be mound-shaped symmetric. Okay, I would say it's okay. It's a little unusual in that there's more data values at the tail than there are in the center. That's a little weird. So if I really wanted to make sure I could run a test for normality, just to check, make sure. And you can see that my p-value is greater than 5%. Which again, I'm not going to reject the null. And the null is that it comes from a normal distribution. So based on the limited evidence that we have here, we can still say that it appears to be mound-shaped symmetric. So our central limit conditions, our central limit theorem conditions are satisfied. So let's run the hypothesis test. So same deal, t-stats, one sample. But now I'm going to do with data. Sorry, because I'm given a raw data set, right? So I click on that, click on my variable. And notice that unlike the with summary where I had to enter all those summary statistics, Excel's going to do all the heavy lifting. It's going to find out the sample size, it's going to compute the sample standard deviation, and compute the sample mean. So all I have to do is go ahead and determine my hypotheses. So I want to test the claim that the mean lead concentrations for all medicines is less than 16. Now, another thing to keep in mind is that inequalities always go with the alternative. Okay. So here, the null is going to be that mu is less than or equal to 16. I'm sorry, greater than or equal to 16. And the alternative will be that mu is less than 16. And again, I can kind of confirm that I'm on the right track, okay? And this is important. One of the things will happen is if you get the test wrong, the p-value will be huge. It'll be above 50%. And that's a sign that you did it wrong. I can test this. In order for this to really be the alternative, for it to make sense, X bar should be less than 16. In other words, my evidence has to favor the alternative. And so when I go ahead and choose this for the alternative, let's see what we get. Okay. So notice that I chose the wrong way. And so you have to be a little careful. The book is not consistent with their use of the word claim. How do I know I chose the wrong way? Because my sample mean is, hold on, let me just make sure I'm doing this right. Hold on a second. All right, the alternative is less than, right. So notice that, let me go through this carefully here. My sample mean is less than 16. Oh, because I'm sorry. I didn't put in the value for mu naught. So when you get really large p-values, check and make sure that you put everything in, okay? You still have to put in the value. In the last example, it happened to be the default, which is 0. Okay, there we go. All right, now we're doing a little better. So notice that I'm testing to see if it's less than 16, the population mean. My sample mean is less than 16. I get a reasonable p-value. So I've done good. We still have to make a decision though. right? So our p-value is about 10%, it's about 9.5%. What is our alpha? Our alpha is 1%, right? So the p-value is greater than alpha. So I'm going to fail to reject the null. If you're having trouble with this step, stop and write this out. Okay? Write out p-value less than alpha, reject the null, p-value greater than alpha, fail to reject, and then think about what that means, okay? But here I'm going to fail to reject. So there's not enough evidence to show. So what we would say at a significance level of 1%, there is not enough evidence to show that the average lead concentration in all traditional medicines is less than 16 micrograms per gram. So that's something that you have to work through and think about. And we've computed our p-value, we computed our test statistic, right? If I go back here, I can see this is my p-value, this is my p-value, right? This is my test statistic, minus 1.4. That's not that far away from 0. Again, thinking about this like an approximate z-score, okay? So it's not that unlikely I could get this value in the population where the mean was actually 16. And again, this is our p-value. Okay, very good. And so you might have to kind of pause this video a lot and think through this and work through this, but this is a good problem to work through yourself to make sure that you really understand it. The one hard part is going to be determining the hypotheses sometimes. And I will admit, I don't like the fact that sometimes they test against the claim and sometimes the claim is the research hypothesis. And you have to think about which is which. Usually when it's from a manufacturer, we test against. Okay? But in this case, this is the research hypothesis. This is what we're trying to show. And again, the way that you can do that is the sample mean has to be consistent with the alternative. That's really important. All right, last problem. So what I want you to do in this problem is to kind of take it apart the way that we did before. You can go ahead and you can read the video, read this problem statement. You can fill out the first 4 pieces of background information you're going to need to be able to do. And then I'm going to have you figure out what the hypotheses are first. So this will be the reading quiz question. So stop the video, read the problem statement, go through these first 4 items here so that you have an idea of what's going on, and then answer the first question as to what is the hypothesis test being tested. Okay, good. So what I want you to do for the last part is to go ahead and run the hypothesis test. Just like we did in problem 3. You can run the hypothesis test and then you can answer the last 3 questions. So pause the video, run the hypothesis test using StatCrunch, and with your output, answer the last 3 questions. Okay, very good. All right. So again, things to do when you're working on hypothesis tests in general, always determine the context. All right. And again, this is something that shouldn't take you long to do. You want to try to understand the context in about a minute. Okay. And it's very easy because when you're working hypothesis tests, like on an exam or a final, you look for percentages or means, right? Percentage of or mean of what? That's your variable. Who are we interested in these values for? That's your population. write it out in one sentence. And that will help you really get your bearings. You'd be surprised at how much easier the problem will be. And then again, assign values to quantities, especially when you're given a summarized data set. Right? This is super important to do. So you want to make sure that you do that and then check the requirements. Okay, and finally form the hypothesis test. And again, the hardest part's going to be when they're asking you to test a claim. All right? And when the claim is equals to, that's easy because the alternative is always not equals. When it's an inequality, it's harder. And the best way to determine unequivocally is to look at the sample mean. And the sample mean has to be evidence in favor of the alternative. So if you're testing to see if the population mean is less than 16, your sample mean better be less than 16. If you run a hypothesis test, a one-tailed hypothesis test, either testing if it's greater or less than, and your p-value is greater than 50%, you probably ran the wrong direction. Then you want to go back and reread it. And I don't think the book doesn't give you any situations, to my knowledge, where they run a hypothesis test and the sample means not in favor of the alternative. That would be a stupid hypothesis test. You would never run that in real life. Okay, I hope that helped. That's a lot of stuff to go through, but I think with this background, you'll be ready for the homeworks and the exams. Good luck.